exclusive. Means that they are separate. Kind of our key word to remember. Okay, that's our keyword is separate here with that mutually exclusive, but we are going to write out a little bit longer definition, which is two or more characteristics that cannot happen at the same time. So when I flip a coin, can a coin be both heads and tails at the same time? No, unless you see those like right, but it can't be heads and tails at the same time. It's either heads or it's tails. Those are mutually exclusive. They're separate things. When I pick a card, it's either black or it's red. Can't be black and red at the same time. Dante, you can keep that away here, friend. Okay, so I'm going to use my highlighter. I'm going to highlight mutually exclusive. Means that they're separate. And separate means that they cannot happen at the same time. So if we think about this in that Venn diagram, if I have two things that I'm comparing, but they're separate, where would those things be described in the Venn diagram? Would they be on the left side, the middle, or the right side if those two things can't happen at the same time? Yeah, it's going to be on either side. There's no middle part, so we're talking about filling it in on this side and on this side. But there's no middle spot. Okay, to find that probability, we're doing a probability of A or B. We're seeing which one of these. We're not going to happen at the same time. It's not A and B. It's not both because it's either one or the other. And to find that probability, we add our probabilities of each together. So we do our probability of A plus our probability of B. Okay, so we're going to do an example of this. And I want to know what's the probability of when I draw a card that I'm going to draw a spade or a red card. So as we look, spade, remember, is spades. That's this one. When I think about spades and red cards, are any of these spades red? No, all these spades are black, so there's no overlap. None of these spades are red. If are any of the red spades? No. Nope, so they're completely separate things. So that's what makes them mutually exclusive. Spades and reds, there's no cards that could be both. Okay? So what we're going to do here is we find the probability of each of these. So I'm going to start by finding the probability of a spade. Okay, and remember, spade is a suit, is what we call it, or a shape. How many of each shape do we have in our deck? Or each? 13. So it'll be 13 out of 52. Or we can think about it as how many shapes is that? If there's 4 shapes total, and how many of those 4 are spades? 1. So 1/4 would be our simplified fraction. Okay, another thing, then we're going to find our probability of our red. So how many cards, 26, yep, are red out of 52? Or we can think of it as how many colors are there in the deck that's split evenly. 2 colors, and red is 1 out of 2. So kind of 2 ways to do that. We can either think of it with that 26 out of 52 or the 1/2. So to find the probability that we have a spade or a red, we're going to add our probabilities together. What was the probability of picking a spade? 13 out of 52 or 1/4 plus, what's the probability of my red? 1/2 or 26 over 52. Either way is fine. Now, when we add fractions, we do need common denominators. So if we did the 13 out of 52 plus 26 out of 52, we could add 13 and 26. Because I use the simplified fractions, we would have to multiply, find common denominator between 4 and 2, which would be 4. Okay, or we can just use Desmos. Desmos does all that work for us, which is really nice. So if I do 1/4 plus, whoops, I want the plus on the side though, 1/2, we get 3/4. Which 3/4 should be a decimal that you kind of have memorized. It's kind of a decimal that happens a lot in math. Does anyone know 3/4 off the top of their head? Good, 0.75 because it's like 3/4. And 0.75 as a percent, 75%. Now if you are still somebody who you're multiplying by 100 to do this, when you multiply by 100 here, I can't just do this last half times 100. I would want to put that in parentheses and then times 100, and it would tell me 75%. Okay, if I just do times 100, that's only going to multiply the half by 100, and I get this crazy number. So if you're going to do times 100, put in a parenthesis sign to make times 100. You get 75%. So is that impossible, unlikely, equally likely, even chance, likely, or certain? Likely, yeah, it's likely that you get a spade or a red. That's the majority of the cards. Okay, and spades and reds are separate, so that was what made them mutually exclusive. All right, I'm going to use my other color highlighter, so if you were using one color, switch the colors. We're going to now talk about not mutually exclusive. So if mutually exclusive means that they're separate, what would not mutually exclusive mean? They're not separate. So it's kind of like we're doing the opposite. So in mutually exclusive, our definition back at the top, mutually exclusive was 2 or more characteristics that cannot happen at the same time. What would be the opposite of 2 things that can't happen at the same time? 2 things that can happen at the same time. So 2 or more characteristics that can happen at the same time. Okay, and big part there is that idea that it can happen at the same time. So if we're talking about outfits, can I wear tennis shoes at the same time as wearing a red sweatshirt? Yep. Could I pick a card that is both red and the number 6? Yeah, are there any of these reds that are 6s? Yeah, we have this red diamond and this red heart. So we're talking about things that have that overlap, that they could be both things at the same time. So if we think about that as our Venn diagram, some of you said it in our warm-up, where does the both happen in a Venn diagram? In the middle. So we're talking about this part, this overlap, where it can be both things. It works for both. And that's our not mutually exclusive, or it works for both. Now, our formulas are a little bit different for this one. Because we have that overlap, what ends up happening is we're going to count the probability of the first thing, which would be this left circle, and then we count the thing of this right circle. But when I count the left circle and the right circle, that overlap we counted 2 times. So we have to take away that overlap once so that we make sure that we only count it 1 time. So probability of A or B is equal to, we do a probability of A plus the probability of B. So just like our mutually exclusive. But when we do that, we count this middle part twice. And we're saying, yep, there's stuff there. So since there's middle stuff twice, we have to take that out once, because we only want to count it 1 time. So we subtract the probability of A and B. So the amount that's both. Before, when we counted it, the left circle and the right circle, it was fine not to subtract because there was nothing in that overlap. We didn't have to count anything there. Here we have to count it. We're going to count it once with the left side, once with the right side. So we have to take it out because there will be that amount that's both. Oh, thank you so much. Ooh, that's perfect for me. All right, so here's our example number 2. We're going to draw a card, and I want to know what is the probability that I draw a face card, or a diamond. Probability that I draw a face card or a diamond. Why do you always have such a weird face today? Alright, so when you look at face cards in a deck, if you need to take a look back here, which ones are our face cards? Queens, kings, and what does the J stand for again?
Joker.
Not Joker.
Jack.
Jacks. So we have our jacks, queens, and kings are our face cards. Overlap there. Do you see any that are both a jack and a diamond? Yeah, the jack of diamonds. Is there anything that's both a queen and a diamond? Yep, a king and a diamond? Yep, so we have an overlap because we're going to be looking at these diamonds and we're going to be looking at these face cards. But because there's that overlap, there's some that share that characteristic where it can happen at the same time. So first thing we're going to do is find our probability of a face card. And I just put face, not face card, because I was lazy. So how many face cards are there in the deck? Okay. Jack, queens, and kings. Yep, we have 3, 3, 3, and 3. So all together that would be 12. So we have 12 out of 52. Do you guys want to simplify that or just leave it? I'm good with just leaving it. You guys are good? Okay, we'll simplify it later. Now I want my probability of my diamonds. So now I'm counting all my diamonds. And we talked about that a little bit earlier with the spades. How many are there of each of those shapes? 13 out of 52. But I have this extra step now. I need to find the probability that I would pick a face card that is also a diamond. And I'm writing it kind of weird because I'm going to run out of space here. So I wrote it kind of big. Probability of face and diamond. So how many are both a face card and a diamond? 3. Which 3 are both a face card and a diamond? The Jack of Diamonds, the Queen of Diamonds, and the King of Diamonds. These 3 were both in those face cards and in the diamonds. So we actually counted those twice by accident. Okay, so we had 3 cards that are both out of how many cards total? 52, the total still. So to find this, what we're going to do is we add together our first 2, and then we subtract that both. So we do our probability of our face card, 12 out of 52, plus our probability of our diamond, which is 13 out of 52, and then we'll take away that amount where it was both. How many cards were both a face card and a diamond? 3 out of 52. So this one was my face cards. This was my diamonds. And this one is where they're both. Now, when I add and subtract, if I have the same denominator, I can just keep the denominator the same, 52. And I can just add my tops or subtract my tops. So I'm going to think, what's 12 plus 13? 25, and 25 minus 3? 22. So we could do it by hand if we want to, if they all have the same denominator. If they don't, you'd either have to find that common denominator or just use Desmos. Or you can just plug it into Desmos right away. That's fine too. If you look at fractions and you're having like a panic attack looking at them, we don't want that. Our goal today is to find probabilities, not necessarily to add fractions. So 12 out of 52 plus 13 out of 22 minus 3, out of 52, not 22. Out of 52. When I hit that fraction button, it simplifies it for me also. So my calculator got 11 out of 26, which is the same thing as 22 out of 52. Because what did they divide top and bottom by? Yeah, they would have divided by 2. So they get 11 out of 26. Okay, we're going to have to round our decimal. Let's do 3 decimal places again today. So if I do 3 decimal places, it goes 0.42307692331. So do I want to keep it at 423 when I round? Or do I want to move it to 424? 23, because what comes after that 3? 0. So 0.423, which then if I round to the nearest percent, is that going to be 42% or 43%? 42%, yep. All right, we're at